Thank you, Dr. Lee.
Oh, no
Hello,
problem.
everyone. Hello, everyone. I'd like to thank National Center for Transportation Infrastructure and Durability and Life Extension for the opportunity to present my work here, titled Performance Evaluation and Load Rating of Impact Damage Steel Girder Bridge. Allow me to introduce myself. I am Mohd Rahman, a PhD student at University of Texas, Arlington. Over last 3.5 years, me and my supervisor, Dr. Nubi Yazdani, and our group are working on health monitoring of bridges in Dallas-Fort Worth area, Texas. Our work includes non-destructive evaluation, load testing, load rating, and suggesting suitable retrofitting options for vulnerable bridges in the TxDOT areas. Today, my presentation is outlined as introduction, problem statement, objectives, non-destructive evaluation, non-destructive load testing, data analysis, load rating, and conclusion. Composite bridge construction have been practiced since 1930s. Many old bridges are not designed for composite action. In non-composite bridge, each structural element bends around its own neutral axis. But in composite bridge, the concrete deck and the steel beams function as a one element to resist the applied load by transmitting shear force between the interface of two elements. Moreover, right now, according to ASC 2021 bridge report card, around 7.5% of total bridges are structural deficient. One of the most common issue for this deficiency is identified as impact damage by vehicles. Impact damage by overhead vehicles may cause spalling, cracking, exposed river, broken rivers in case of concrete bridges, whereas in case of steel bridges, it might cause local or global buckling or piercing through the structural members. Here is an example how impact damage occur in a highway bridge. For this study, such an impact damage bridge was selected. The name of the bridge is San Francisco Bridge. The bridge is located east of Dallas, downtown Texas. The bridge has 6 spans and symmetric about the center line of the bridge. The spans are 30 feet, 60 feet, and 70 feet, respectively. 60 feet and 70 feet spans are continuous. The deck thickness of the bridge is 6.5 inch and the girders were wide flange 33 into 130. So in November 2017, the bridge was impact damaged by overhead vehicle. You can see on the screen that the part of the vehicle is raking through the concrete deck and piercing through the girders. So prior to non-destructive test and load testing, a field visit was conducted. Upon field visit, a lot of cracks and potholes were observed on the concrete deck, and moreover, the damage girder performance will be different from the undamaged girder. Hence, it is necessary to understand the overall behavior of the bridge so that efficient and reliable methods can be applied to such bridges. Objective of this study, to evaluate the performance of the impact damage bridge through non-destructive evaluation and static load testing, propose a distinct approach to load rate non-composite concrete deck over steel girder bridges by incorporating ND data in the load rating procedure. Non-destructive evaluation consists of two parts. First, use of ground penetrating radar, GPR, to detect river spacing and river cover. Second, use of impact echo to determine delamination in the concrete. So GPR data was taken along the orange line parallel to the traffic, whereas impact data was collected on each square grid points. Load testing. This is a plan view of a bridge instrumentation for load testing. Only continuous spans are instrumented in 6 different sections. A total 28 strain gauge and 12 rotational telemeter are installed on the steel surfaces. Top and bottom strain gauges are installed on the inner surface of the top and bottom flanges of the girder. Rotational telemeter are installed to capture the end rotation of the girders. A static load test was performed on the continuous span. Because that span was hit by the override vehicle, two different tracks were used in this purpose. Both crawl space test and stop location test were performed according to ASTO manual for bridge evolution. Four different paths were predetermined to capture the effect of each girder due to live load. For example, for path 1, girder A and B will have higher response compared to girder C and D. And for path P3, girder B and C will have higher response compared to girder A and D. After that, data analysis, a 2D contour plot of top reinforcement cover depth were developed by post-processing of GPR data. Approximately 62% of the examined deck have cover range varying from 1.5 inch to 2.5 inch. And to verify the GPR data results, actually concrete was drilled on the concrete deck to verify the GPR data results. Similarly, for IE data results, IE on the discrete grids are plotted on a 2D contour maps. Red indicates severe delamination, yellow indicate moderate delamination, and blue indicate no delamination. For load test, the response of the girders were recorded by strain gauge. Left figure is a sample run for girder on girder B and C. Girder B and C responded higher compared to other girders as expected. From neutroaxis analysis, they showed the presence of unintended composite action between the concrete deck and the steel girder. These might arise due to self-weight of curve, railing, or deck, creating adhesion or friction. So here on the right side of the screen, you can see the theoretical non-composite theoretical neutroaxis from the bottom of the girder is around 16.55. And from the experiment, we got 17 to 18 inch from the bottom of the girder. Load rating. Bridge load rating provides a basic for determining safe load carrying capacity of the bridge. The load rating was determined using the presented equation on the screen. It is capacity minus dead load divided by live load, comprises with different factors from ASTO manual for bridge evolution. As the bridge is non-composite, so we have to load rate each of the structural element. So we separately do the load rating for deck and girders. For deck rating, GPR data was used to find the concrete cover and river spacing for negative milestone near the girder lines. And from impact echo data, the percentage of delamination, both negative and positive zones, are found. So here is the result for deck rating and girder rating. So in both ratings, inventory level, in both level, inventory and operating level, we can see the rating factor is less than 1. So which means the bridge is unable to carry HS20 load. The rated vehicle is HS20 because that one is preferred by TXDOT. So as we can see on both the rating, deck rating is lower, so the bridge rating is governed by the deck rating, which is around 23,000 pound. Conclusion: the GPR data indicates around 17% of the scan deck area has a top cover more than 2 inch. In light of greater clear coverage than specified, the moment capacity of the deck is compromised. IE contour plot demonstrate the integrity and the strength have been compromised in the concrete deck. Load test data confirmed the presence of non-composite action. At inventory and operating levels, both the concrete deck and girders are unable to carry HS20 load. As the deck rating was the lowest, so the bridge rating was governed by the deck rating. Thank you everyone for your patience hearing. if you have any questions, or if you have any questions in future, shoot me an email. I'll happy to help.
Thank you.
Thank you.
Any questions?
Yeah, I have a question.
Yes.
Yeah, so when your impact happens and the deck is not a composite with the girder, have you studied how to make it composite?
Yeah, I mean, we leave that part for the retrofitting options. So this is just the load testing part. So yeah,
Awesome.
we know how to make it composite, like putting shear stud on the deck between the interface of deck and girders. That part is for the retrofitting options.
So you're going to do it?
Yeah, like we'll suggest different kind of retrofitting options to TextDot, and that final decision is based on TextDot.
Okay.
So what they decide, yeah.
Thank you.
Any other questions? Okay, thank you very much.